Imagine deploying an app to Kubernetes and suddenly nothing can talk to anything. Pods are running, containers look healthy, but the whole system behaves as if every component is stranded on its own lonely island. Today we are fixing that. Because once you understand Kubernetes networking, services, ClusterIP, NodePort, LoadBalancer, and Ingress, the entire platform finally clicks into place. Welcome back to the channel. If Kubernetes has ever felt confusing, especially the networking part, this is the video that will finally make it simple. By the end of this breakdown, you will understand how Kubernetes networking actually works, why pods can talk to each other without NAT, what services really do behind the scenes, the differences between ClusterIP, NodePort, and Load Balancer, how Ingress becomes your elegant, scalable traffic controller, and the exact mental model used by cloud engineers and DevOps professionals. And I promise you this, once networking makes sense, the entire Kubernetes world opens up. Let's jump right in. Kubernetes networking often appears complicated, but only because it involves several moving parts. So let's begin with the fundamental challenge. Pods are ephemeral. They come, they go, they restart, and their IP addresses change constantly. If you try to connect directly to pod IPs, your system will fail regularly. A single crash, a rescheduled event, or even a routine rolling update is enough to change a pod's IP address and break the connection. So Kubernetes needs a networking model that solves three core problems. First, every pod must be able to communicate with every other pod. Second, pod IPs must be routable and no overlapping across all nodes. And third, applications must have a consistent, reliable way to be reached, both internally and externally. Without this, microservices simply could not scale. Kubernetes answer? A flat pod network paired with stable services and a smart external entry point called Ingress. Pods become disposable, access becomes stable, traffic becomes intelligent. Let's break it down piece by piece. Before we even talk about services, you need to understand the foundational rule that makes Kubernetes networking possible. Every pod gets its own unique IP address, and pods can communicate directly without NAT. This is one of the most important design decisions in Kubernetes. There is no host-level NAT to deal with, no port mapping hacks that complicate deployments, and no manually managed bridge networks that you need to configure or maintain. Regardless of which worker node a pod runs on, Kubernetes ensures the following. First, the pod network is flat. Second, all pod IPs are reachable from any other pod. Third, pod IPs are unique across the entire cluster. And fourth, networking remains consistent even if a pod moves to a different node. That's why CNI plugins like Calico, Flannel, and Cilium exist. They maintain a unified cluster-wide flat network. But here is the catch. Even though pods can communicate directly, you should never rely on pod IPs as stable, long-term addresses. Pods are temporary by design. They will terminate, they will restart, and their IPs will inevitably change. So you need something stable in front of them. And that's where Kubernetes services come in. A service is Kubernetes' way of saying, give me a stable, reliable, never changing address to reach this group of pods, no matter how often they restart. A service performs three critical functions. First, it creates a permanent virtual IP address inside the cluster. Second, it uses label selectors to identify the correct set of pods. Third, it load balances traffic across all healthy pods. That's it. Simple, powerful, essential. Instead of connecting to pods directly, everything else communicates with the service. The service determines which pods are alive, which node they are running on, and how to distribute traffic efficiently. Now let's move on to the most important service type, ClusterIP. ClusterIP is the simplest and most widely used service type in Kubernetes. It exposes your application internally within the cluster. That means other pods can reach it reliably. Internal microservice to microservice traffic flows through it. It serves as the stable point of communication for that application, and it cannot be accessed directly from the outside world. Most cloud-native systems rely heavily on internal communication. Front-end to back-end, back-end to database, API to worker pods, authentication service to user service. In all of these cases, ClusterIP provides the stable identity for your application. If pods dies, restart, or move to another node, the ClusterIP remains the same. It's essentially like giving your application a permanent phone number, even though the actual phones keep changing. But what happens when users outside the cluster need access? That's where NodePort comes into play. NodePort exposes your application to the outside world in the simplest possible way. Kubernetes opens a port between 30,000 and 32,767 on every worker node. Any request sent to NodeIP:NodePort reaches your service. Then the service forwards traffic to your pods. The path works in the following order. The request comes from the external client, reaches the node's IP, then flows through the NodePort, continues to the cluster IP, and finally arrives at the pods. NodePort is easy to understand and quick to set up, but it's a bit of a brute force solution, and it comes with some serious trade-offs. Here is why NodePort isn't recommended for production. First, you are forced to use those strange, high-numbered ports instead of nice, clean ones like 80 or 443. Second, you are effectively exposing every node in the cluster to the internet. Third, there is no built-in cloud-aware load balancer doing smart work for you. Fourth, if a node fails or your DNS isn't set up carefully, you can end up with ugly edge cases and broken access. NodePort is great for small clusters, internal tools, labs, or quick debugging. But for real user-facing applications, you will want something better. That's where Load Balancer comes in. When you are running Kubernetes in the cloud, such as AWS, GCP, Azure, DigitalOcean, and so on, you will almost always reach for service type load balancer. Here is what happens behind the scenes. First, Kubernetes asks your cloud provider to create a real load balancer. Then, that load balancer gets a public IP address. Next, external traffic hits this cloud load balancer. After that, the load balancer forwards traffic to your Kubernetes service. And finally, the service load balances requests across your pods. It's clean, it's scalable, it integrates perfectly with the cloud. This is the standard way to expose production applications like APIs, web front ends, and gateways. But there is a big catch. Each service of type load balancer creates its own cloud load balancer. Expose one app, no problem. Expose 5 apps, still okay. Expose 20, 30, or 50 services this way. Now you are paying for 20, 30, or 50 load balancers, and that adds up quickly. This is where Ingress becomes a massive upgrade. Ingress is the elegant solution to exposing multiple services through a single external entry point. Because instead of dealing with things like one cloud load balancer for every single service you deploy, multiple public IPs you need to manage, and all those confusing external routing rules, you simply rely on one load balancer, one Ingress controller, and a clean set of routing rules that handle everything for you. Here's the idea. First, your cloud provider gives you one external load balancer. Then that load balancer sends all incoming HTTP and HTTPS traffic to the Ingress controller running inside your cluster. And finally, the Ingress controller looks at the request and routes it to the right service based on the rules you define. Ingress rules come in two main forms. Host-based rules, for example, api.example.com or www.example.com. These let you route traffic based on the domain name the user is trying to reach. The second form is path-based rules, such as /blog, /admin, or /checkout. These let you route traffic based on the specific URL path. And the beauty of Ingress is this. You can have one domain, one public IP, one load balancer, and still run many different services behind it, each with its own routing rules. Ingress gives you several powerful benefits. Smart, flexible routing, so traffic always reaches the correct service. Clean URLs and real domains, making your application look professional and easy to access. Centralized HTTPS termination, meaning TLS is handled in one place instead of across multiple services. Simplified certificate management, because you no longer need to manage certificates for every individual services. A much cleaner overall architecture with fewer moving parts and clearer traffic flow. And finally, significantly lower cloud costs, since you replace multiple load balancers with just one. This is the standard pattern used by real-world Kubernetes deployments, especially those running lots of microservices. Just remember one key point. Ingress is not a service. Ingress doesn't replace your services. It works alongside them. It uses your existing ClusterIP and load balancer services to expose them in a way that's clean, scalable, and easy to maintain. Let's build a simple mental model that ties everything together. Pods are the temporary workers. They run your containers, they do the actual work, but they come and go, and their IPs change all the time. Services, especially ClusterIP, function as a reliable interface that keeps your pods accessible regardless of IP changes. NodePort is the quick and dirty way of opening the door to the outside world. It works, but it's not elegant or scalable. Load Balancer is the cloud-native way to expose a service with its own public IP. Your cloud provider creates the load balancer and handles the heavy lifting for external access. And Ingress functions as the centralized traffic management layer, directing incoming requests to the appropriate services based on defined routing rules. So the real traffic flow in a typical production setup looks like this. Traffic begins with the user, then moves to the cloud load balancer, which forwards it to the Ingress controller, which then routes it to the appropriate service. And finally, the request reaches the pods that handle the workload. Once you view it this way, Kubernetes networking stops feeling like a mysterious black box and instead reveals itself as a clean, well-structured, layered system. Here is everything we covered in one place. Pods receive IP addresses, but they are ephemeral. You should never rely on them directly. Services provide stable and consistent access to pods, even as those pods are continually created and destroyed. ClusterIP manages internal communication between microservices within the cluster. NodePort exposes applications externally through node-level ports, though it comes with several limitations. Load Balancer integrates with your cloud provider to deliver production-grade external access through a dedicated public IP. Ingress adds intelligent routing, domain management, centralized HTTPS termination, and cost-efficient scaling for environment with many services. Understand these 6 core ideas, and Kubernetes networking stops being confusing. It becomes predictable, powerful, and surprisingly even enjoyable. If this cleared up Kubernetes networking for you, hit the like button so more people can find this video. Subscribe to AI Guru for more practical, high-level engineering content, and drop a comment below. Which Kubernetes topic should I break down next? Thanks for watching, and I will see you in the next one.